2, 1. So one-dimensional distance, position, and displacement. So it's one of the introductory components in physics when you're walking into grade 11. So let's take a look. So when you walk into physics, hopefully your teachers are going to give you a little bit of a background, but the main component that you're starting off with is most likely kinematics. And what does that word actually mean? It just simply means the study of motion. And motion in general just means the change of a location. So you can change the location from one point to another. But in kinematics, the key distinction between studying kind of motion in other ways is that we're not really interested in what causes the motion. So that's what you can see there in brackets. I put that we're not interested in what causes this particular motion or this change of location or possibly direction, but we are just interested in studying the motion itself. And typically that study will start off with talking about distances and displacements. So those are the two key components, and then you can throw in position in there as well. So let's take a look at these particular topics. Now, distance in general, okay, so something that you have been most likely exposed to, and I have actually done a pretty lengthy video on this particular distance because it's a foundational component of physics. I'll put it up above there. And here, my interest is going to be talking about the distance, okay, and trying to give you kind of a general first look at example of how this concept of distance, then it pushes over into position and displacement. All right, so distance as a definition just means that you're trying to measure the length, okay, of a path that you are starting from one point and then ending at another point. So you'd want to be able to know how long that particular path is. So a very easy way, because we're just in one dimensions, is to view this, and let's say that we have, okay, one-dimensional kind of a grid as I have right here, and let's say that you are starting, okay, at this particular point. So this is maybe your home or your starting position, and we will give it a reference point, right? So we always have references in physics in terms of these distances, positions, and displacements, and I'm going to call this that, I'm going to start this off at 0, okay, and this particular distance, okay, I'm going to say that it's starting off at 0 meters, meaning that this is kind of the home starting point. Now, if you're trying to measure a particular distance, let's say you're walking now somewhere, so you maybe are going to be walking over, and I don't know, let's say maybe you walk all the way over here, and that is 1, 2, 3, 4, 5. So maybe let's say this is 500 meters, okay, and right here maybe there's a little grocery store. All right, so you have a little grocery store sitting up there, okay, and here's a little sign, okay, so this is the grocery store that you have. Now, if you walk this particular distance, okay, and you go all the way over here, you know that you have covered a distance of 500 meters. Now, you can of course continue, so maybe a little bit later on, I don't know, maybe somewhere over here, there's a little bike shop over here, okay, that you have, and now you're going to be continuing to walk. So you walked your 500, okay, and then you walk, okay, additional meters over there, and as you can see here, this is 800 meters, okay, with the respect of my starting position, right? So in total, if you've walked this distance, you would have walked over here, and then maybe you've walked over here, so that would have been 800 meters. Now, if you continue walking, and let's say you walked over here, and then you went over there, and then you come back all the way, then you know that you're going to be walking in total 800 meters one way and 800 meters another way. And that would have been 1,600 meters in total. So that's a distance because you're traversing a path from one point to another. And this particular path, we can measure how long it is. Now, of course, distances have units, and here I've used meters. And this is something that you should be aware of, that for distance, which we typically will abbreviate with a D, okay, so within this D, okay, so that you have your actual unit, you have many units that you can measure this in because it will depend on the distance you're traversing. So maybe if it's an ant walking by, maybe, I mean, sure, you know, ants will definitely are capable of walking 500 meters, 800 meters, but maybe their distances that they cover around the nest that they live is maybe not that long. So we might use centimeters, maybe millimeters or something of that nature. But in physics, we always have a standard unit. So this particular standard unit, we sometimes call the base unit, and is when you're studying this in grade 11, you most likely are going to be studying this, okay, in terms of the metric standards, right? So sometimes you'll see the symbol SI, which just means Standard International. So this is kind of the standard, just like you have a grammatical standard in English. Well, you have also a standard in terms of units. And because there are so many, you know, we pick a specific unit, and that unit is meters. Okay, so shorthand, we just use M for an abbreviation to be able to measure those particular distances. But you can measure them in kilometers, in miles, right, in feet, and you can do unit conversions back and forth, okay, in between there to bring it back to a standard unit. So that is the distance that we travel. Now, those distances that we have, if you know, had a friend and maybe that friend was somewhere in a different location, okay, than you can't really tell the friend, okay, so well, you know, maybe you might want to walk to your grocery store and it's 500 meters. Well, you don't know if it's 500 meters to the grocery store from where your friend is located. And even if it was, okay, that particular friend may be on the opposite side, right? So maybe that friend is actually, you know, standing somewhere all the way over here. So maybe, you know, your friend is standing somewhere over here, okay, and that is its reference point, okay? So, you know, his or her reference point now in terms of walking, well, it might not be actually, you know, 500 in the same direction. So in your direction, as we have drawn this in one dimensions, so we can think about directions. For example, going west, right? Going east. So in this case, you know, if you're moving along, you're going to be moving east. Your friend is going to be moving west in the opposite direction. You can, of course, go north and south. You have other types of directions. Sometimes you use a compass, which, you know, you have it with degrees, right? So where you're going, okay, in terms of with respect to maybe the north, okay, and south and west and east and so on. Sometimes we call those directions just simply going up, right, or down, or going to the right, okay, and going to the left. So all of these directions do matter. So distances just measures the length of the path that you have taken from one point to another. But if you want to start to let somebody know where to go, you're most likely going to be also needing direction. So in physics, we start to combine these. And what we do is we have a combination between, for example, the actual distance and the direction itself. And when we combine the actual distance that you cover, right, and then you provide a direction, you may want to start talking about a particular position. Now, position, be careful, because it's not the actual distance that you cover. Position just means where are you with respect to a reference point. So for instance, if your reference point, okay, so as we have it, is your home and you're standing here and you're starting your reference at 0, if you want to be able to locate where your friend is currently standing, so that friend's position we would write in a little different way. So we wouldn't actually call it a distance anymore, so we would call it a position. We make sure that we give this little symbol of an arrow above, okay, for position. And what it means is whenever we give a direction, okay, we start talking about vectors. So vectors have both a magnitude, okay, and a direction. So we call this the magnitude, okay, and for us, in terms of distance, would be the actual length from a reference point, and then the actual direction would be where that object or that person is with respect to a reference. So this particular friend, okay, of ours, as you can see there, so if the grocery store, so because I've counted, and each little square, so from here to here was 100 meters, so 100, 200, 300, 400, 500, right? So 600, 700, 800, 900, 1000. So the position of your friend that you have is 1000 meters. And now you would have to give it a direction. Typically, maybe we'll give directions in terms of square brackets, although not necessarily. We sometimes might leave a space. And this friend, okay, of yours, it looks like they are about 1000 meters east. All right. And this is a position now. Okay, so this is now a position because now you know the location of where your friend is. Your position would have been just 0 meters, and it wouldn't necessarily have, okay, an east or a north, okay, or south or anything like that, or up and down, because you are at the origin, at the reference itself, right? But these two are actual positions. The grocery store, okay, that you have would have been 500 meters east. The bike shop would have been 800 meters east. Now, if we had something else, right, so maybe planned out, okay, so somewhere, I don't know, somewhere over here, okay, so as you're kind of walking through, so there's a bike shop, so maybe, you know, a cell shop, okay, so a cell phone shop. So this particular one, in terms of its position, we would have said is 1, 2, 3, 4, 5, 6. Okay, so this would have been at 600 meters, but now this one would have been to the west. So assuming the left-hand side is the west, and then the right-hand side is the east, okay, as we were moving along. Okay, so this one-dimensional path. So that is a position that we actually have. And positions are always with respect to a reference. If you move your reference, then that would change, okay, the actual positions that you have. So the 0, okay, so the reference point of where I'm standing, okay, if I take that and I say, well, no, I don't want that to be my reference. Maybe where my friend is, that will become the reference. Then that's going to change, obviously, okay, all the different magnitudes that I have. Because where my friend is standing, the bike shop is 200 meters west, right, of where my friend is standing. So if that reference is where my friend is, then that would have changed my actual reference. So the position is basically the location. And if you're ever driving and you're looking at the GPS, that is a reference with respect to our Earth itself. Typically, we have local references. So here, I'm talking about a local reference, okay, with respect to a person that we have. Now, I've mentioned vectors, right? So these are kind of measurements that we take of, physical quantities that we have. And all of those vectors will have some kind of a direction. If you drop the direction entirely, and then there is no direction at all. So for example, distance, because you're just kind of wandering around and wanting to know, what is the length that you covered from one point to another, and you're not interested in the direction that you're going, well, those distances or those kind of quantities are called scalars. So scalars just simply have a magnitude, right? So they just have a magnitude, while vectors have a magnitude and a direction. Okay, so a position is a vector, because it has the distance from a reference, which is the magnitude, and then it has the actual direction from the reference, where it is. Is it west, is it east, north, or wherever it might be, or maybe you're using a compass. So that's what you have within here. So those are distances, right? Directions, positions, scalars, and vectors. Now, scalars and vectors in physics, they play an enormous role, because we're not just interested in a magnitude of something. Very often in physics, we're going to be needing the direction, because we want to be able to know, right? It's the same thing as you telling your friend where to go. You can't just give your friend, go 500 meters and then you'll get to the grocery store. you would have to let that person know in which direction they would have to go, right? So you can say that the grocery store, is 500 meters west, okay, of you, okay? So that would have now given it a position. So the grocery has been now positioned so your friend knows, okay, where to go. Now, the last item, okay, within here is displacement. And displacement is actually kind of crucial. And it is different than the actual distance itself. So a displacement that you have, okay, is the change of the actual location or of the position, right, that you have experienced from a starting point, so basically an initial starting point to a final starting, okay, or ending point that you have. So for instance, if you would take, okay, and let's say, you've walked all the way, and this is a little bit tricky in the sense that if you're walking and you got to the grocery store and then you walked all the way to the bike shop, you've walked 800 meters, right? Now, if you're talking about a displacement, then what you would have to do is you would have to do the following. You would say that your displacement, which is typically the change, so this little triangle just means change, okay, in the position vectors. So what is your final? Now, final, I'm going to write F, okay? What is your final position minus your initial position that you started with? So what is the change? So for you, if you're talking about walking all the way through to the bike shop, your final position, right, because the bike shop was located at 800 meters east of you, so that was the position the bike shop was at, minus your initial position, your starting point was just 0 meters. Okay, now this one doesn't have necessarily, because it's your reference of 0, doesn't have a direction there. But you can clearly see that if you now try to subtract and you're walking along this, then you would have walked 800 meters in total, and you would have gone east. So your displacement captures the actual distance that you had in a direction. But there is a little bit more, so we have to be careful, and I'll give you examples of this, okay, in just a moment. So when you are talking with regards to your displacement, so this one is easy because you started at your initial, okay, starting point. So this was your displacement is 800 meters east. And if you were looking at this, right, so with respect to this, so let me just copy this down, okay, as best as I can here. Let me just capture maybe the whole thing right there. So if you had this, I always like to kind of capture this by these arrows, and these are kind of vector arrows. So you know that you would have walked all the way over here. That's your final, right? And so we call this actually the tail. So that's the tail. It's a starting point. And this is the head, okay, or sometimes the pin, okay, of the vector itself. So it captures in one dimension kind of the entire length, right? And then you can see where the direction goes. It points with respect to the arrow. Now, for us, this would have been our final position vector. Our initial position vector basically is here stuck at 0, so it's not moving anywhere. But let's imagine now that what you've done is the following. Let's say that you've walked, all right? So now you have been walking, and you actually did walk all the way to the bike shop. But then you started to walk back, and then you said, okay, I'm going to go back to the grocery store, which is going to be in a different direction. So now you want to talk about what is the displacement, right? So what's the actual displacement that we would carry out here? Well, the displacement here now can be drawn, and I'm going to do it in 2. We have our final vector, so we've walked all the way through, okay, as you're going through from one to the other, But if I would draw these vectors, right, so this is the other one right there. So we've walked in one direction and then we've walked in the other direction. So what is the total displacement? Now, you might think, okay, well, it's 800 meters, right? Plus an additional 300 meters. So that would have captured your distance. So your distance would have been your 800 meters plus another 300 meters that you walked, which would have been 1100 meters. But that's a distance that you have. And now for your displacement, okay, as you're carrying through, so if you wanted to see what this entire thing was, then you have to be careful, because as you're going through, your displacement is captured. And if you look at these two vectors, okay, and you started to go in, you're going to be adding them together, but they're in different directions. So you have one displacement, so your total displacement that you have, so total, let's put T. It is a vector, so for vectors we always put a little arrow up above. And for that, as you're going through, you had walked one displacement. This is the displacement all the way up to the bike shop. So that's your first displacement. And then you've walked another displacement right here. Okay, so this is now going back to the grocery store. So now when you're adding these two together, you might fall, into a little bit of a trap in here, of thinking about what the displacement is. And I don't want you to get confused, with respect to this, because that's not going to be the answer. The answer actually is, so within here, this is the resultant vector. So this is the resultant vector. So this is when you are adding this one. So as you're going through and then you come back over here, notice that your final position, is all the way here with respect to the reference that you had. So the result of these, as you were adding them through, so this one, that particular one, was 800 meters, and this was, 800 meters, and this, as you've gone through, was actually east, plus, now displacement number 2, so be very careful there, because that displacement number 2, as you're going through, is going to be, so you were starting at the bike shop, right, and then you were ending, at the grocery store right there. So the actual difference, so the final, right, minus your initial for your route number 2, which is this route right here, is as you're going through here. So this is your, your final was 800 meters, and this was, 800 meters. I apologize there. So because your final one is you're ending up at the grocery store. So your grocery store is 500 meters. And this one was with respect to, and 500 meters east, minus, and this is going to be 800 meters east, because that was your starting point from going from the bike shop to the grocery store. And notice that this is minus 300 meters east, right? Because you're going in now the opposite direction. So notice the minus, actually just tells you, that you're no longer east. It is actually 300 meters west. So these two are the same, because that sign just tells you that you're going in the opposite direction. So these two are identical. And notice that if we substituted, so if we had this and we substituted it back into here, right? So if I substituted this and, put 300 meters, now if I put west, right, or negative 300 meters east, which when I add these up, my result between the 800 meters and this is actually 500 meters, right? So that would capture this particular vector. So my displacement is 500 meters east. So that's what would have happened over here. And that's what the displacement will do. So the displacement is actually a vector, and it just kind of captures with respect to how you're moving along, okay, what that is. And I love to always capture it by these, right? By these particular arrows that you have. So for instance, it's always the resultant. So if I'm going to remove this right here, so let me delete this out. Let's say now we're talking about your friend, okay? And then your friend is now moving along. So let's imagine that, your friend, okay, so goes all the way up to, right? So it goes all the way up to the cell shop, okay, all the way over here, okay? And then, your friend decides to come back, right? So from here and then visits you over here, right? And you want to know what the displacement is. So visually, I like drawing these particular, vector kind of little diagrams that we have, because it allows us to see what the resultant is, okay? So the resultant vector is basically what happens as a result of this, your friend going all the way to the cell shop and then coming back. Well, the result is that your friend, okay, so all the way over here, okay, this would have been the actual vector as a result for your friend. So they have covered, okay, so the distance that they've moved is all the way from one point, okay, and then all the way over here. So if you wanted to calculate the distance, you would have to say, okay, so that would have been 1,600, right, because it's 1,000 to you and another 600 to the cell shop. So 1,600 plus another 600 to walk to you, which is 2,200 meters or 2.2 kilometers. That would have been the distance. But the actual displacement, okay, that we would have had, notice that we're going to the west, right? So the displacement as you're going from here, so this is from this point over here all the way to this point. Okay, and then here, because it's very visual, we can count it up. So that would have been 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we knew that this was going to be, okay, 1,000 meters. Okay, and notice that it's to the left. So this is the displacement that overall, okay, your friend would have had, which is different than the actual distance, okay, that you carry. Now, going back in here in terms of displacements, okay, and also kind of terminology with regards to how we label these. So just kind of to summarize, for distance, okay, it is a scalar, and we abbreviate it typically with a D. Now, some teachers, and especially I got caught off guard, okay, and when going into post-secondary, some will actually even abbreviate it with an S. And you see that, I put that over here, especially for displacement. The S, okay, is spatium, and it comes from Latin, and it means just space. But for us, especially in high school, you typically will use just distance. So just be careful, whoever is writing these out, and don't be surprised and shocked if people do use, okay, little s, okay, instead of a little d for these. Now, position is a location with respect to a reference point, and it is a vector, so it needs a direction. Displacement right here, okay, is the actual change in position from what it was initially to what it is final. And in order to capture them, we can capture them by using vector diagrams. And these vector diagrams, okay, so where they start, this is the tail, the starting point. Where they end is the head or the pin. And you can draw them, and especially in one-dimensional, okay, ways, and you can find what the resultant displacements are. And you can directly count them up if you have a nice grid, right? Or you can label them and then you can know. So here, if I would label these throughout, if I know that this was 1600 meters, right? This was 600 meters. Notice that they're in opposite directions, so I would subtract them and I would get my 1000 meters right here. All right, so there you have it. Okay, so that is the introduction to these distances, positions, and displacements that you have. I have as a final, okay, here, a little example for you. Okay, so this example is nothing to do necessarily with walking along, you know, between your friends, grocery stores, bike shops, and cell phone shops, but it is more, okay, in terms of a blood particle traveling through the human body. So let's see how we can capture this. So you have tracked the particle for 25 seconds and noticed that the particle went up to the brain, which is 35 centimeters from the heart. Okay, then it came back to the heart and was pumped down to the foot, okay, which is 1.4 meters away, okay, from the heart. So now we have two questions. You can pause the video and try to see, okay, if you can answer these questions, and then you can come back to the video and I'm going to solve these. So how would I do this? So this basically just summarizes what we have tried to do. So here's my pieces of given information, right? So this is what I have. Now I love to draw these kind of body diagrams, so these diagrams of what is happening, okay, overall. So within here we're talking about a blood particle, so I can certainly do that. Now it doesn't have to be, you know, on a grid, so let's imagine that we don't have a grid. All right, so there you go, so no grid, so let's see what we're gonna do here. So we have, okay, so here's, you know, I'm going to draw kind of a stick man in here. So let's imagine that's, you know, me or the person, right? So here it is, you know, here's kind of that. Let's assume that this was the foot, okay, over here. You know, so here's the arms, okay, over there. Let's assume that our, you know, heart, okay, so heart is going to be, okay, somewhere there. And now let's take a look and see what they're saying. So they have 35 centimeters. So the particle is actually moving, right? So it goes from here. So let's, okay, kind of this is the distance. So it goes up to the brain, all right? And this is supposedly 35 centimeters, which is the same thing as 0.35 meters, right? So that's just a prefix there. So that goes up there. Then it starts to come back, right? So let's put this in a different color. So now it comes back over here. And then it is pumped down all the way to the foot. All right, so there you go. So now it's pumped down all the way to the foot. So I'm just drawing these vectors, right, that I have. And that is 1.4 meters away. So 1.4 meters away, which is the same thing as 140 centimeters. So there you have it. Now, what was the total distance traveled by the blood particle? Well, the total distance, okay, in here, so our distance that we have is equal to, so notice it's going to be 35 centimeters, which it went up, okay, 35 centimeters that it came down, and then it traveled 140 centimeters, right, in total to go all the way through. So that's the path that it has taken. Remember that distance is a scalar, right? So there's no directions. We just are interested in, okay, kind of what the actual path was. So if you add all of this up, the 35, so that's 70. 70 plus 140 is 210 centimeters, or, okay, 2.1 meters. And I think keep answering meters. All right, so we'll keep it in meters here. So that would have been the distance traveled. Now, what was the displacement after the 25 seconds? Okay, keep answering centimeters. Well, the displacement is different, right? Because the displacement is going to be with respect to a reference point. So we need locations. So here, you know, so our reference point, so let's say this is our starting point, our origin, 0 centimeters or 0 meters, right? So this is kind of our reference point here. And now notice, so the heart goes up and comes down. So in this path, right? So as it goes up and as it comes down, right? So this first trip going up and down, the displacement over here and coming back over here, that displacement on that particular path right here, let's call this displacement, right? So the change, displacement number 1 to go up and down is actually 0 meters, right? So because it comes back, right? So we're back and stuck over here. So that actually all cancels out. So really now for the entire trip, my displacement as a whole, so here's my other trip, okay, going all the way there. So my displacement over here on that second trip is the actually total displacement. So if this is my trip number 2 of the particle, which is going to be 1.4 meters. Now notice this is down, right? So we need a direction. So in this case, we're going to point down, right? So down with respect to our reference, because we're going, okay, in a down direction. So now my total displacement that I have in here, so T for total, okay, and we put a little arrow above for the actual item there in terms of the vector. So that's 0 meters, which is from the first one, plus the 1.4 meters down from the second. Well, that's very simple for us to do. So indeed, it's going to be 1.4 meters down, right? Which is definitely much different than our actual distance, which is covered. So that would have been the measurement for our displacement. Now they want it in centimeters, so we can certainly change it to centimeters, which is 140 centimeters down. And that's how you would calculate these. So I hope that now you can see the difference between a distance and a displacement. All right. Okay. Thanks for watching. Hopefully we'll see you in a future video. Bye, everybody.